Hello everybody, so I'm going to kick us off in the open source channel talking about containerization and the COVID-19 surveillance effort. So my name is Kelsey Florek. I'm the Senior Genomics and Data Scientist at the Wisconsin State Laboratory of Hygiene, and I'm also a steering committee member of StaPH-B, and I'll talk a little bit about what that is in just a second. So bioinformatics is an umbrella term that kind of encompasses a number of different fields, including computer science, biology, and statistics. And so you can kind of think about this like data science, where the domain knowledge in this case is biology. And there's a number of barriers in place that preventing bioinformatics from taking place in public health laboratories. There's a vast landscape of compute infrastructure across public health, various on-prem servers or workstations. Some laboratories have access to institutions that can provide access to things like high-performance compute clusters or public cloud. And then some laboratories just don't have any infrastructure to work with at all. And so it can be a real challenge to kind of bring in data analytics and bioinformatics into some of these instances. Additionally, a lot of these laboratories have limited experience working with open source software, and limited informatics support beyond typical like desktop or network support. So when it comes to a public health laboratory trying to adopt and bring on board sequencing, surveillance, and genomics and bioinformatics, there's a lot of challenges around these things. So StaPH-B, which stands for the State Public Health Bioinformatics Work Group, was kind of built with this idea of how can we build resources and projects to kind of overcome some of these barriers. So things like providing training, support construction and infrastructure, building up infrastructure for some of these public health laboratories, and partnering with the Centers for Disease Control Prevention and the Association of Public Health Laboratories to make sure that whatever we're doing it to a best standard or best practices, and that things are getting implemented in a way that makes sense. So with these barriers in mind, and with things like training and experience, you might already kind of recognize, in this being a Docker community all hands event, Docker is actually a really big part of our efforts. So several years back, Curtis Kapsek and I kind of put together this idea of what if we took a lot of the bioinformatic tools that are really important, that are open source, and created images of all of these into a central location that were developed in a way that would make sense for public health laboratories. And Curtis has done a phenomenal job in maintaining this resource and keeping it going throughout this pandemic. And I really cannot thank him enough for all of his effort on this. And it's turned out to be a really valuable resource. So this project has 90 different open source bioinformatic analysis tools that we've containerized and packaged together. Things like data QC, genome assembly, so taking fragments, sequencing read fragments and assembling them into a complete genome, annotation, and things like classification, so determining what kind of variant is there, as well as relationship between those variants and other variants. So that kind of gives a real high-level picture of this project and how it fits into public health. But I really want to focus on this idea of coronavirus variant surveillance, because that's where we've seen a huge benefit of containerization and really leveraging a lot of the tools that we use in the US and global surveillance effort. So real briefly, I kind of just want to walk through what the process actually is. So we get a sample from a clinic or hospital into the laboratory, we extract that genomic material, that RNA in this case, convert it to DNA, fragment it. So we take those long genomes, those around 30,000 base pair genomes, break them down into a bunch of fragments and sequence those fragments. So we end up with these fragments of the genome, up to millions of them, and we have to assemble them back into its original genomic shape. And so we do that by looking at either mapping those fragments to their known locations or looking at overlaps between those fragments. Then once we have a genome, we can do all kinds of different analyses, and even there's an effort to make those sequences public so that we can start sharing as part of the national and global surveillance effort for things like developing vaccination or just monitoring variants of concern as they move throughout the world. So I wanted to kind of highlight a couple of the workflows that have been developed that really leverage this Docker project that we put together. And so the first one I want to mention is developed by Dr. Erin Young from the Utah Public Health Laboratory. It's called Secret, off of the Secret Lake in Utah. And this is, as you can see, it's a fairly complex workflow. And one thing I really want to highlight here, for those of you who are coming from this from like a services aspect, the way we utilize Docker containers is actually a little bit different than how most people might interact with them. So rather than running a tool or application as service within a container and having it running the entire time, we actually kind of create these containers and destroy them as needed for different steps in the workflow. So as reads are being brought in and analyzed, containers are being created and destroyed, and the idea is that each tool is running within its specific environment, and we can kind of pull things off the shelf and implement them as needed. Another great workflow that I want to kind of point at is developed by Theogen Genomics by Kevin Libwitt, Dr. Robert Petit, and Frank Ambrosio. And the real benefit to the workflows that they've developed is, I mentioned that a lot of public health laboratories don't have access to compute infrastructure. And so they've done a lot of work in trying to leverage public cloud and UI interfaces to make these workflows a little bit more accessible to laboratories. And it's done a phenomenal job in making sure that all of the laboratories in the US, regardless of if they have the compute infrastructure or expertise to run these things, they can still leverage all of these containerized applications and still perform surveillance. And kind of talking about that and just showing how much of an impact this has had, in March, we started seeing an increase in the number of polls on some of these images. And so Curtis kind of made an announcement and said, hey, look, we're getting a number of interest in some of these containers, notably the ones most associated with coronavirus. And then 7 months later, it was quite incredible to see as more labs started bringing on coronavirus surveillance. We started to see more and more polls, and it got to a point where, we've been regularly impressed with just how much of an impact this library of tools has had, and it's been really phenomenal to see so much growth and development in this area. So that's kind of this aspect of what's kind of the workhorse for this surveillance effort. But I also want to talk a little bit about coronavirus itself, evolution, and how we're kind of tracking this over time. So I would be remiss as a bioinformatician not to share a phylogenetic tree. And coronavirus itself kind of mutates around 2 positions or 2 mutations per month across its genome. And so when you look at this figure, what you're looking at is the lines that connect each dot to each other dot. And each dot represents a virus selected from the global surveillance effort. And all of the variants of concern are colored in different colors. And anytime we sequence a virus and want to understand its relationship to other viruses, the easiest way to do that is to construct a tree. So you take all of these samples, you put your sample in with it, you build a tree, which is a very computationally intensive task, and you end up with an idea of how your virus is related to every other virus. However, this is totally impractical if you ever want to try to do this on a regular basis. This is really kind of a, take a sub-selection and perform this analysis, but it's not really a way to have global surveillance efforts surrounding it. So during this pandemic, researchers at University of Oxford and University of Edinburgh developed this tool called Pangolin, which instead of building a tree every time we wanted to look at a particular variant, the idea was, what if we used a machine learning algorithm to classify that virus and its mutational pattern in accordance with everything else that has been seen so far. And so the idea is, with this tool, it can be done in a much quicker fashion, and it gives you a hierarchical notation that lets you identify where that virus came from. So you might have heard of something like B117. That's the actual Pangolin notation that tells us what the history of that virus has been or what its evolutionary history has been. And this has been an incredibly valuable tool, but as you might imagine, with a machine learning algorithm, the model has to be trained and up to date with the new viruses that are being seen. And so it can be really tricky to kind of maintain your workflow as this tool is continuing to develop. And again, Docker to the rescue here. By containerizing this tool with all of its dependencies, Curtis has done a fantastic job maintaining this and keeping us going through the pandemic. And so the way it's been able to work is we develop our workflows to utilize this tool. And then as new versions or new updates come out, Curtis packages them and releases them. And we know that whenever we run our workflow, as long as we're using the latest container, we're always running the latest models that have been validated and are ready to go. And so it's been a phenomenal resource to keep everybody that's doing any kind of coronavirus surveillance on the same page. So I wanted to step away with a few takeaways from this talk. Containerization solves many problems in bioinformatics, specifically around the distribution of open source software. Being able to containerize the tool within its environment and all of its dependencies has been huge. Repeatability, making sure that if I construct a container or an image and I give it to somebody else to run, I know that it's going to run in the proper way and they're not going to run into issues. And it really simplifies the development of workflows, being able to abstract away the tool itself and think about what my inputs and outputs are. It's been phenomenal for trying to develop these really complex workflows in a short amount of time. I really want to emphasize just how much infectious disease surveillance and research is really built on open source. Everything I've talked about today, all of the figures I've shown, have all been developed from open source software, tools, and things like that. And we just would not be anywhere today without a lot of the open source efforts that are happening. And containerization has just been instrumental throughout this pandemic, allowing a wide range of laboratories with various capabilities being able to contribute to this global surveillance efforts, which has huge impacts on things like vaccine development and just tracking and risk assessments of what do we need to do from a public health standpoint. So if anything that I've talked about is interesting to you, or you think you might be able to contribute in some way, APHL and CDC has partnered to create this bioinformatics fellowship. It's been a great opportunity to kind of get into a public health laboratory and really start doing some of this work. A lot of the people that I mentioned have been part of this fellowship, and they've been phenomenal in developing all of these different resources and tools for StaPH-B. And so for that, I would like to say thanks to the entire StaPH-B community. They've been a phenomenal community to work with. And I'd love to highlight them all, but I can only highlight a few. So here's all the people that have contributed to the Docker project itself. I wanted to give a special thanks to Ava and Aurelian for inviting me to speak at this event and really kind of organizing everything, as well as a thanks to Association of Public Health Laboratories for all of their support and effort going into this, as well as SPEARS, which is the US consortium of academic and just industry, commercial, federal laboratories that have kind of all come together and to share knowledge and approaches to dealing with this coronavirus pandemic. So if you have any questions, I would be happy to take them in the chat, and thank you so much for listening.